Hi everyone. Today we'll take a look at Euler's form and we'll look at operations of polar coordinates also. All right, so Euler's form, right? So it is quite similar and it's based off from the previous video when I talked about polar form. So every complex number, right? Every complex number can be represented as in this form that I'm going to talk right now. Can be represented in the form, and I'll write it right here. So I'll put an arrow. I'll put z is equal to r e raised to the power I theta. Okay, and where cos theta plus I sine theta. Let me rewrite this. So cos theta plus I sine theta is equal to e raised to the power I theta. Okay, so in this case, what we have is we have our modulus, right? Our modulus of the complex number is r. Our argument is theta, and our conjugate, right? Our conjugate is I would say it would be z bar is equal to r e raised to the power I minus theta, right? That's all that changes. So let's now look at the relationship between polar versus Euler form, right? So let me change the color to yellow, and I'll write polar versus Euler's form. Right. So we have our normal complex number in our polar form, which would be r times cos theta plus I sine theta, right? And this can be basically written as r e raised to the power I theta, right? Where this changes, cos theta plus I sine theta can be written as this. And then we have our conjugate, which is r cos theta minus I sine theta is equal to r e raised to the power minus I theta, right? So this is the relationship between both of them, right? And now for those who really curious how we get this, right? I'll just show us a quick derivation of it as well. So if you want, you can skip this. I'll put in the timestamp. So if you're not really interested, you can skip it and you can just use the actual conversion that I've stated. But okay, so if you want to look at it, how we derive it, right? So I'll say how we derive it, right? So we're going to use the Maclaurin series. Now, if you haven't heard of that, it's okay. It's usually something you learn at the very end of calculus. So Maclaurin series is basically an expansion, right? So we expand a certain function in a different manner, and what we get is a pretty accurate representation. So let me explain what I mean. Suppose we have the graph, or we have the function e raised to the power x. Now we know e raised to the power x is an exponential function, right? We know it's something like this. Now if you want to represent it in another way, we can do it by Maclaurin series. So the series expansion for e raised to the power x is 1 plus x squared upon 2 factorial plus x cubed upon 3 factorial, and so on and so forth. So actually, the further you go, right? The further you go, and the further you, and then if you put this in the calculator or any Desmos or any other software, what you're gonna get is a small function. Maybe the function will only be like from here to here or something like that. But it's only from this to from -1 to 1. It's gonna be a very accurate representation of the actual function. So maybe in your free time, what you can do is maybe plot e raised to power x on Desmos, and then plot maybe 1 plus x squared plus x cubed, maybe to the power 5 probably, and then you can see how accurately till at when x is equal to 0, how accurately it plots the function. So yeah, so we can ignore this part basically. So I'll take this out, and now let's talk about the series expansion, right? So we have this expansion right here. Now let's also talk about the expansion for sine and cosine, right? So for the expansion for sine would be x minus x cubed upon 3 factorial plus x to the power 5 upon 5 factorial minus x raised to the power 7 upon 7 factorial, and so on and so forth. And for cosine, it is 1 minus x squared upon 2 factorial plus x to the power 4 upon 4 factorial minus x raised to the power 6 upon 6 factorial, and so on, right? So just if you guys don't know this, these expansions are in your data booklet, so you can check them out later. I think it should be the very end of the data booklet in the HL section, right? So now if we expand just e raised to the power x, right? And let me do it in a different color and on a different page. So I'll take peach for that. And if I expand e raised to the power x, right? So I know I already have the expansion of e raised to the power x, but I'm going to replace x with I theta, right? Because that's what we have right here, I theta. So I'm going to replace x with e raised to the power I theta. So what I'm going to get is e raised to the power I theta is equal to 1 plus I theta, right, in brackets. I'm just wherever I see x, I'm going to replace it with I theta. So I'm going to get I theta whole squared upon 2 factorial plus I theta whole cube upon 3 factorial plus I theta to the power 4 upon 4 factorial plus I theta to the power 5 upon 5 factorial. I think that's enough for now, and so on, right? So now when I expand this, right, and you can do the math later on your own if you're not satisfied by my explanation. What you can do is you can expand this, right? I squared is minus 1, I cubed is minus I to the power 4 is 1, and so on and so forth, right? What you're going to get is you're going to get some numbers with the iota, some numbers without the iota. So obviously the numbers without the iota are real numbers, numbers with the iota are the imaginary numbers. So we combine the like terms, we add up all the real terms and we add up all the imaginary terms. So what we get is we actually get 1 minus theta squared by 2 factorial plus theta to the power 4 with 4 upon 4 factorial. And then we get, well, this actually kind of goes on. I don't want to close it off exactly, that's good, that would be incorrect. So it kind of goes on to infinity, and then I close it off, and then I'm going to write iota, right? And then I'm going to have is theta minus theta cube upon 3 factorial plus theta to the power 5 upon 5 factorial plus all the way up to infinity, right? So now if you were paying attention, you realize that the first expansion right here, right, this expansion is exactly like the expansion right here. So let me take my laser, change the color. So you'll see this, right? This part is exactly like this part, okay? And this one is identical to this, except for x we have theta. Obviously that's just a variable change. Besides that, nothing has changed, right? So maybe I'll put this in green, so I can write basically the expansion of cos theta, and put this in blue and I'll write expansion of sine theta. So now I can rewrite this as, let me change the color again, so I can rewrite this as e raised to the power I theta is equal to, I'll bring back green, all right, cosine of theta plus, and then change the color again, put I of sine theta. And we basically got our original, statement that we wrote right here, right? We got this, right? It's the same thing, right? So this is the essential derivation of how we even, convert from polar to Euler form, right? I mean, it's not exactly necessary, but it's nice to know, at least you get a feel or an intuitive feeling for what's actually happening here, right? Okay, so now let's look at one more small thing, which is the Euler's identity, right? And then we'll look at more properties. So before that, let's look at Euler's identity. We scroll down. Okay, so we have the Euler's identity. Okay, so the Euler's identity is quite simple, right? Let me write the Euler form and the polar form in this case, right? So I'm going to write cosine of theta plus I sine theta, right? Now if I replace theta with pi, right, then what am I gonna have? E raised to the power I pi, right? I'm gonna have cos of pi plus I sine pi. Okay, Now, I know cosine of pi is -1 and sine of pi is 0, so I can write this as e raised to the power I pi is equal to -1 plus 0. Thus, e raised to the power I pi is equal to -1, or we can say, e raised to the power I pi plus 1 is equal to 0. And this is quite an important result that we have got here. It's a standard result, and you might have seen it before, maybe on some cool videos on math, or maybe your professor or your teacher must have talked about it. But yeah, this is really important. E raised to the power I pi is equal to -1, right? It's a very important standard result that you will need to use multiple times, right? Obviously, if you don't memorize it, if you do forget it, you can always use the conceptual knowledge, right? Okay, so I know e raised to the power I pi can be written as this form, and then I'll evaluate this form. Obviously, you can do that, no issues, right? But this is an important result, and I highly suggest that you try to just memorize it. It's not some rocket science thing, right? So yeah, these were like the small little concepts. So now let's look at a few example questions. All right, so let's look at this example. So we have convert 5 e raised to the power I 3 pi by 4 into Cartesian form, right? So let's talk about the general process before starting, right? So the first step, what we do is would convert Euler form to polar form, right? Polar form, and then convert polar form to Euler form, right? And this will be like the general steps every time you do it, right? This will be the general approach, I would say, every time you find a question like this, right? Honestly, this is way too simple to be a question, right? I don't think this will ever come in any exam, right? So, but these questions are just there for your general understanding, develop your concepts. So, nevertheless, let's try solving it, right? So, what I said was we're going to convert Euler to polar, right? So, 5 is our r, or I would say our modulus, right? That's our first thing, and we have our argument as well. Our argument is 3 pi by 4, right? So we have these two things already, right? So let's convert now what we have to polar form. So we know what we can write this like this, and then we have, okay, let me, before that, actually, what I'll do is I'll write the general form here. So I'll scroll down here, and I'll write e raised to the power I theta is equal to r times cosine of theta plus I of sine theta, right? This is what we have. And I know our r is 5, so I could replace r with 5. And I know our argument is 3 pi by 4, so I'll write 3 pi by 4 everywhere. So here, I sine 3 pi by 4. Right, so now let's just evaluate what we have, right? So we're going to have 5, and cosine of 3 pi by 4, well, 3 pi by 4 is in the second quadrant, and so cosine will be negative, so it's going to be -1 upon square root of 2. And I sine 3 pi by 4, well, that's sine is positive in the second quadrant, and it's 3 pi by 4, so it's plus 1 by root 2, right? Now let's just basically distribute the 5, so we'll have -5 by root 2 plus I of 5 by root 2. So now we have essentially, plugging in by plugging in the value of our argument, we've converted the entire thing to Cartesian form right here itself, right? So we have our Cartesian form, right? There's nothing to do. So this is our Cartesian form, and basically we have answered the question. So it's as simple as this. And so when you're also working backwards, right, it's maybe from Cartesian to Euler form, what you do is obviously you find the modulus, right? You find the modulus, and then you find the argument, and then you just write it here because you have the you just need the modulus and the argument, right? So the modulus and the argument. It's as simple as that. Let's look at a few more simple example questions, then we'll look at little bit more complicated questions. All right, so we have a question that is asking us to draw the complex number in the coordinate system given by the modulus and argument, and to find its Cartesian equation, right? Cartesian equation in the sense that they want to start in the Cartesian form, right? So a better way of saying this would be in its Cartesian form. Okay, so let's draw it first, right? So let me draw the coordinate system. I'll change the color, and I'll take white. So A very rough sketch is enough. You guys don't need to, make a scale drawing of it either. Just create a very rough sketch. So we have a modulus of 5, and its argument is 5 pi by 3. So 5 pi by 3 is in the fourth quadrant, somewhere here, I would say. Somewhere just, I'll say approximately here. Draw a stromal arrow, draw a dot, and we can say this is r is equal to 5, right? And this angle is 5 pi by 3, right? So we have our information right here. Okay, so we have plotted it successfully, right? I'll just put it as z naught or something, right? We don't have to worry about that anyways. Now the main part is to find its Cartesian equation. So if we can do it multiple ways, right? Well, I mean, not really multiple ways, but there are multiple approaches. But I'm just gonna follow the standard approach which I did in the last question. So first, what I did was I converted it into polar form, and then from polar, I just plugged in the values of theta, and I got in my Cartesian equation. So let's go ahead and do that only, right? So I know e raised to power I theta is r e raised to power I theta is equal to r times cosine of theta plus I times sine of theta. So I have my modulus as 5, right? So 5 times cosine of theta is just cosine of 5 pi by 3 plus I times sine of 5 pi by 3, right? Now all I have to do is just basically evaluate this, right? So I'm going to have 5. I know 5 pi by 3 can be written as minus pi by 3 because remember, it's this whole circle is 2 pi. So I know this is minus pi by 3. I can rewrite it this way. So I'm going to have is cosine of minus pi by 3. And the reason I do that is because it just helps, keeps things as simple as possible. And especially if you're, if you just learn trig, it just helps, keep a very nice, compact, thinking system. Anyways, I mean, if you have memorized the values of 5 pi by 3, you can go ahead and plug it in. Honestly, I did not memorize any values up until like grade 12 or something. Like I used to use the unit circle and just, remember the sides and then the angles, and then I used to work, but it's okay. So I know cos of minus pi by 3 is cos of pi by 3, which is half. And sine minus pi by 3 is minus sine pi by 3. So I'll put a minus sign outside, and is equal to square root of 3 by 2. If I distribute the 5, I'm going to have 5 by 2 minus I of 5 root 3 by 2. So this would be my final answer in terms of Cartesian form. And if you think about it, we go 5 by 2 units right here, and then 5 root 3 units down. So it's the same thing, right? Let's just look at one more small example. Okay, so we have the question, convert the complex number minus 1 plus I root 3 to Euler form. So the Euler form is what? E raised to the power I theta. So r e raised to the power I theta, right? So where r is the modulus of our complex number, right? Modulus, and theta is the argument of our complex number, right? So basically, if we have these two values, we can go ahead and convert into our Euler form, right? So z is equal to this. So let's find the modulus first. So we have modulus of z is equal to square root of the real part plus square root of the imaginary part. So minus 1 whole squared plus square root of 3 whole squared. So modulus of z is 1 plus 3. Modulus of z is equal to 2, right? So that's our modulus. We have found that. Now let's find the argument. So to find the argument, you can do it multiple ways, right? You can use your proper math formulas and find it. But I always like to use it. I always like to think about it conceptually and graphically when finding the argument. So what I'm going to do is I'm going to actually graph it, right? I'll show you the second approach right after this, but I'll show you what I prefer doing first. So I have my plane right here, and it says minus 1 plus I root 3. So minus 1 plus I root 3. So somewhere around here, right? But I'm not gonna make this one. I'm gonna increase the size just so it's easy to see. Right, somewhere right here. So I have my thing right here. What I'm gonna do is I'm gonna draw this line, right? And I'm gonna draw two perpendicular lines as well. So what I'll do is I'll change the color of the other line. So I'll draw it in lime, and I'll draw something like this and something like this. Right, so I have my lines right here. I know this is minus 1, and I know this is root 3. Okay, and I have to find basically the argument, which is this right here, theta. So now this is my point, right, set. Now, how do I find this theta? If I find this angle, alpha, right? What I can do is theta is equal to pi minus alpha, right? It's as simple as that. So let me go ahead and find alpha. To find alpha, what I'm going to do is I'm going to ignore the sign here. I'm just going to take the magnitude, right? I'm going to take the magnitude and I'll change the color again. So if I have to find the magnitude, what I can do is I can find the magnitude, right? Just square root of 3 and upon minus 1. I'll do like this, tan inverse, or hold up, I kind of screwed this up. So tan inverse all of this, and my theta is equal to this. Sorry, my alpha, right? My alpha is equal to this. So my alpha will be tan inverse square root of 3, which alpha gives me as pi by 3. Now I have this value memorized, obviously, and as the more you practice, you'll also remember what tan inverse square root of 3 is. So I know my alpha is pi by 3, so therefore my theta is 2 pi by 3. So the alternate approach could have been that you just do tan inverse of minus square root of 3, and then you would have gotten two values because tan can be negative in two quadrants, right? So one value would have come in the second quadrant and one value would have come in the fourth quadrant, and you take the according, you take the respective value which comes in the second quadrant, right? And that's my argument of set, right? So now converting this back into Euler form, what I'm going to have is z will be 2 e raised to the power I 2 pi by 3. Right? That's it. Right. So now let's look at just one more example question. Right? And this example question is slightly out of the box. So if you have not revised your complex numbers, if this is the first time you're doing it, you might find this to be a little difficult. But if you're using this video as a revision method, then you should be able to do this question. So the question is quite simple. Right? It's nothing too crazy, I would say. So it says if complex number z is minus 2 e raised to the power I minus pi by 3, then find its modulus, its modulus and argument, right? That's it. We're being asked to find the modulus and its argument, right? That's it. Now, it's quite simple, right? I mean, all we have to do is just look at this. So this is our modulus, right? If you look at the general form, what do we have? Z is equal to r e to the power I theta. So our modulus is minus 2, and our argument, or our theta, is minus pi by 3. And that should be our answers, right? No, this is incorrect, right? This is incorrect. That is not the answer, okay? This is why it's kind of out of the box question. And I'll tell you why. What is our general form? Our general form of Euler's, in the Euler form, is r e raised to the power I theta, where r is actually modulus of z. And what did I tell you about modulus in the previous video? Modulus is always positive, right? It's always positive, right? This is the information right here. But what we have is a minus 2. So minus 2 is not positive, so we can't use that as the modulus. So that is the constraint that we're stuck with. So what do we do now? And I'll tell you exactly what we do. Right? I'll make some space right here. Right? I'll create a line right here. Create a line right here. So I'll use the space right here. Okay, so we have minus 2 e raised to the power I. You know what? I'll forget that as well. So I'll just work on minus 2. So minus 2 can be written as what again? It can be we can write this as minus 1 times 2, right? So now we have a plus 2 right here. So we can use this. But what do we do with the minus 1? That's the question right here, right? That begs the question. So what I'm going to do is I'm going to use this property, or the standard result, right? All the way up here. E raised to power I pi is minus 1. I'm going to plug it in for minus 1 right here. So what I'm going to do is I'm going to write minus 2 is equal to 2e raised to the power I pi. Now, going back to the original situation, right? So what we're going to have is now z is equal to 2e raised to the power I pi times e raised to the power I minus pi by 3, right? Minus pi by 3. Now, you can see this is a plus 2. So now our modulus is also plus 2, right? Our modulus is not minus 2, right? Our modulus is not minus 2. So now our r is 2, right? That is what we have. Now it's time to find the argument. Well, we have two things, right? We have e raised to the power I pi and e raised to the power minus pi by 3. Well, if you remember your properties of exponents, we apply the same properties here. Nothing changes. So when we have the same base and exponents are different, right? Same base, exponents are different. We just add and subtract them, right? So they're being multiplied, so we add them. So what do we have? So we're going to have e raised to the power I pi times e raised to the power I into minus pi by 3 is equal to e raised to the power I pi minus pi by 3, right? I mean, technically it's pi plus minus pi by 3, like this. And then this is going to give us pi minus pi by 3, which is e raised to the power I 2 pi by 3. That's what it is, right? So now this is our final result, right? So now our final complex number can actually be written as 2 e raised to the power I minus 2 pi by 3. And so here, our modulus, right? Our modulus or our r is actually 2, and our argument of z is actually 2 pi by 3. So you can expect something like this maybe in your exam, something of this sort, where you actually have to think, right? Obviously, the initial thought, you would have thought that, oh, it's just minus 2 minus pi by 3. No, question is answered. But no, right? There's a little bit more to it because this is a conceptual question, because it asks you to focus on the small details, and that's what the IEP is going to ask you to do as well, right? They're going to check you on, or they're going to test you on the small details. Do you remember the small concepts that build the entire chapter? And this is what the question, beautifully asks us to do, right? So these were a few example questions, and I think the last one pretty much summed it up really well. So now we're going to take a look at some operations of complex numbers. So first of all, we have our addition, right? So in addition, what you have to do is you have to convert to Cartesian. You have to convert to Cartesian. So you need it in this form: z is equal to x plus iy. You cannot use the Euler form or the polar form to add two complex numbers, right? Now let's look at subtraction also. So for addition and subtraction, I'll just club them together. So for addition and subtraction, right? For addition and subtraction, you have to convert it to Cartesian form and then and then do the addition and subtraction. But for multiplication and division, you can use polar or Euler, or you can use your Cartesian form. It doesn't matter. But the whole idea of using polar form or the Euler form is in multiplication and division, because it condenses everything. Like I said in the previous video, it condenses everything. I mean, it's so much easier to see e raised to the power I theta compared to x plus iy, right? It just helps, and the math also becomes easier because now we have exponents and we know properties of exponents, right? We use the same exact properties when multiplying, when dividing, when you're raising an exponent to another exponent, right? It's the same properties that are being applied. So when we're multiplying, right? So multiplication, right? So when we have multiplication, so if we have two complex numbers, right? Z1 is equal to a plus I with a b, or if I write this, as in the Euler form, we would have r1 e raised to the power I theta 1, and if you had in polar form, you'd have r1 and then in the parentheses you'd have cosine of theta 1 plus I sine of theta 1, right? I'm going to write it like this only because it condenses everything, right? So that's our goal, to condense and keep things as simple as possible. And we have another complex number now, which is x plus iy, and we have that can be written as r2 is equal to r2 multiplied by e raised to the power I theta 2. So when we're multiplying this, obviously if you're going to multiply this, you're going to have to use a FOIL method, ideally, right? So you have first, outer, inner, and then the last ones, and then you're gonna have to combine the like terms as well. But multiplication with Euler form is so much more simpler, because what happens here is, I'm going to change the colors before. So I'm going to keep this in green, and I'm going to keep this in peach. or I'll keep it in purple actually. So purple. So now what we have is z1 times z2 essentially gives us, right, r1 e raised to power I theta 1 times r2 e raised to power I theta 2, right? And then if I simplify this, right, if I simplify this, I'm going to get r1 times r2. I'm going to club all the like terms together, right? Or I'm going to club them together so they're together, you know? So r1 times r2, and then I'm going to have e raised to power I theta 1 plus theta 2, right? That's all. Theta 1 plus theta 2. Basically, I theta 1 plus I theta 2, but I'm gonna factor out the I and just multiply theta 1 plus theta 2. That's it, right? So that is our final, result. So I can write this as Z1 times Z2. And, if you want, I'll rewrite it again, but in the same color, so it's easy on the eye, because it can get a little weird. So I'd have R1, R2, e raised to the power I, theta 1 plus theta 2. That is my final result. Right? It's very, very simple, nothing too crazy. Right? Now, division. Right? Now, I'll change the color again. Take beige. So we have division. And I'll use the same, ideal equations right here. So division. What do we have? Z1 is A plus IB. Z2 is X plus IY. Right? And then I'm going to write Z1 is obviously R1 e raised to power I theta 1. Z2 is R2 e raised to power I theta 2. Right? So that's what we have. And obviously, if you have to do Z1 upon Z2, we would have A plus IB upon X plus IY. And now that we have a complex number in the denominator, we're going to have to multiply and divide by its conjugate, get rid of the conjugate, and then simplify the numerator because we have A plus IB times X minus IY in the numerator, right? So instead of, doing all that, we can simplify it really easily, right? We're going to have R1 e raised to power I theta 1, and we're going to have R2 e raised to power I theta 2. So now we can separate the moduluses, right? Moduli, I would say. And then all we have is I times theta 1 minus theta 2. And let me just explain really quickly. I mean, I don't think I need to explain if you know your exponent rules, right? If I take the exponent up, right, because it's positive here. So if I take it up on the numerator, I would have negative. So then I would have, I would have negative, right? And then I'm technically multiplying these two. So I'm doing theta 1 plus negative theta 2. Which is why I have this negative sign, right? So this is another standard result like the multiplication one. And you can note this down as well. So I'll basically, circle them in green. And I'll circle this one in green as well. Right, so these are two main instances where Euler form is really, really useful, right? I mean, you can do that. You can use your Cartesian form, or you can even plug it into your calculator if you have a scientific calculator, right? But if this is a paper one question where there is no calculator, what are you going to do? You're going to have to. Then the best option would be to convert into polar form and then work your way out. And then maybe what you can do is maybe there can even be an instance where they want the answer in the Cartesian form. So what you can do is you're given the question in Cartesian form and you need the result in Cartesian form. But the complex numbers are so complicated. What you do is you convert into polar form. You condense it. It's so much more simple. You do your math. You get your final answer, and then you convert it back to Cartesian form, right? Remember, paper one is a no calculator paper. So the answers will always come out to be really nice numbers. So if they don't come out to be really nice numbers, that is a hint for you to know that, okay, I've messed up somewhere here or there, and I need to, check what I messed up on, right? It's only in paper two where you have a calculator that you'll get really, really weird numbers. You might get like 3,758.57. I don't even know, right? But in paper one, you'll get really, really nice and numbers that proper whole numbers, even 0, 1, pi by 3 whatsoever, right? So ideally, this is what multiplication, division, Euler form looks like. Again, we're following basic exponent rules. So if you feel like you're kind of struggling, just go revise your exponent rules from grade 10 or grade 9. That should be more than enough for you to solve these questions. Let's see if we can do a few more example questions with these two. All right, so we have the question. Calculate the following product of this complex number, and this complex number. So before I start the solution, I recommend you pause the video and try it on your own. Now, before you try it on your own, I would just like to point out one small thing, right? Just be very observant right here. If you haven't noticed, let me point it out for you. We usually have we usually have our polar form in terms of cosine theta plus I sine theta. But here we have sine theta plus I of cosine of theta, right? So cosine and sine have been interchanged right here, right? These two have been interchanged. So note that you cannot evaluate it the way you normally do, because because there should be a cosine here and there should be a sine here. So your first goal or your first target should be to how do I convert back to the form of cosine theta and I sine theta, and that goes for every single one of these complex numbers. Until you can't do that, you cannot move forward, or you cannot use any other, or you can't use the Euler form, you can't do anything, right? So that is the first goal. I highly recommend take 10 minutes, take 15, even 20 if you have to. But try to think about it. Like this part, the converting part is pure trigonometry. So like I said before, if your trigonometry is weak, or if you haven't done it yet, you will struggle in complex numbers, because majority of the complex numbers deals with trigonometry, right? So go ahead, try it on your own, assuming you've given a go at it. So I'm going to start explaining what to do now. So I'm going to break each one of them up one by one. So I'm going to color code them. I'm going to give this yellow, I'm going to give this lime, and I'm going to give this orange, right? I've color coded all of them. So let's start with yellow first. I have sine pi by 12 plus I cosine pi by 12. Now, how do I convert this? And the convenient thing is that both angles are same. So now if you remember the property, sine theta is equal to cosine of pi by 2 minus theta, or cosine theta is equal to sine of pi by 2 minus theta. I'm gonna use this identity in every single one of them. Okay, so if I use the identity, what do I have? I have sine, so my sine will turn into cosine, and it'll be pi by 2 minus pi by 12 plus I sine pi by 2 minus pi by 12. Now, if I simplify this, right, what do I have? I have cosine of pi by 2 minus pi by 12, which is basically, this is 6 pi by 12 minus pi by 12. 6 pi minus pi is 5 pi by 12. And the same will go for the other one as well. So we have I sine 5 pi by 12. So that's what I have, right? That is my first uh, complex number simplified, right? Now let's look at the second one. I'll take it in green now. So I take it in green. We'll have basically sine of pi by 6, sine of pi by 6 plus I of cosine of pi by 6. And if I convert this, I'll have cosine of pi by 2 minus pi by 6. I'm using the same thing again and again, right? I of sine pi by 2 minus pi by 6. Simplifying this a little bit more, I'm going to get 3 pi by 6 minus pi by 6. So I'm going to have 2 pi by 6, which is pi by 3, right? So cosine will be, let me just double check right here. I don't want to make a mistake. Otherwise, I'm gonna have to restart. I'm gonna have to check over basically every time, right? So 3 pi by 6 minus pi. So 3 pi minus 2 pi is pi by 6, which is pi by 3. No, not pi by 3. Hold up. 3 pi by, so just a second. I'm kind of having a brain freeze moment, so please bear with me. So 3 pi, sorry, so 3 pi by 6 minus pi by 6, which is 2 pi by 6, which is pi by 3, right? So pi by 3 plus I sine pi by 3. And then my final thing, so which will be in orange, which is sine pi by 4 plus cosine of pi by 4. So sine pi by 4 plus I times cosine of pi by 4. So I'm going to have cosine of pi by 2 minus pi by 4 plus I of sine pi by 2 minus pi by 4, right? If I simplify this, what am I going to have? I'm going to have cosine of pi by 4 plus I sine pi by 4, right? So these are my final basically final complex numbers simplified, right? After simplifying every single one of them. Now I just have to multiply them. So multiplying them, I can just use the property of the Euler form, right? Theta 1 plus theta 2 plus theta 3. Modulus of all of them is 1. Clearly, you can see because there's it's empty, right? So we can say the modulus of each complex number is 1, right? Now, one more thing I want to point out right here. If it's not too obvious for you, let me just, just discrete, or not discreetly, I would say explicitly point it out. So I'll take it in blue. So you know how we have basically, if we have z1 times z2, we basically do r1, r2 e raised per I, theta 1 plus theta 2, right? So we can also do that similarly in polar form as well. So if we have, cosine of theta 1 plus I sine theta 2, and they're being multiplied with each other, cosine of theta 1 plus I sine of theta 2, sorry, this was theta 2. And if I'm multiplying these two, I can basically write this as cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2 as well, right? So these are interchangeable, right? Because think about it, right? I mean, if you convert it back to if you converted this form, theta 1 plus theta 2, this is the argument, right? It always remains the same. So instead of converting it to polar, wasting my time converting it to polar, I'm just going to leave it at this, right? So what I'm going to do is I'm just going to use this form instead, right? As a change, just so you know that you can get the same answer. I'm going to do that as well. So you guys are satisfied as well. So if I go ahead and do that, I'm going to change the color to beige, right? I'm going to have basically, I'm going to add up all the arguments, right? They're all the same everywhere. So I'm just going to do 5 pi by 12 plus pi by 3 plus 4. So essentially I'm going to have, so I'm just going to do that first. So I'm going to 5 pi by 12 plus pi by 3 plus pi by 4. So if I do that, I'm going to have 12 plus 12 because that's the least common denominator. Obviously, 5 pi will remain as it is. I'll have 4 pi here, 3 pi here. So 5 pi plus 4 pi, 9 pi, 9 pi plus 3 pi is equal to 12 pi, which is equal to just pi, right? So my final argument is actually just pi. So what I'll have is cosine of pi plus I sine pi. So sine pi is 0, cosine of pi is -1. So -1 is my final answer. That is it. That's my answer. Now, what if you had converted to polar form, you would have got something like, you would have had something like e raised to the power I pi. And then you know that obviously e raised to the power I pi is a standard result and it's equal to -1. So you would have gotten the same answer here. But what if you didn't have pi? What if you had pi by 3 or pi by 4, right? Obviously, it doesn't strike as quickly. You can't, very quickly say, oh, e raised to the power I pi by 4 is whatever, right? So at the end of the day, if you had e raised to the power I pi by 4 or any other angle, right, you would have had to convert it back to this, you would have had to convert it back to polar form and then evaluate it from there. But because I just kept it in polar form, even if I had to evaluate it, I could have done it easily without wasting my time, right? So these are the small things as well that you have to keep in mind. When is the appropriate time to convert? When is not the appropriate time to convert? Because those are, at the end of the day, those also take up some time, right? They take up minutes. They can even take up to 1 minute or 2 minutes, especially if you're doing paper one, right? And the whole idea is to become so efficient at the end of the day when you're writing the exam paper, that you should know, okay, if I can't do this method because I'm going to waste a whole lot of time doing it, and there's a chance that I can even miss attempting a question which I could have gotten full marks on, right? So these are the small things you need to keep in mind. Obviously, they're not going to happen overnight. They're going to happen as you do more questions. You're going to get an idea, okay, I'm more comfortable in doing this method and not in this method, so let me work with it, right? Right. So yeah, this was all for today's video. So today we discussed, Euler form and polar form, their comparison. We looked at different questions, starting very basic questions and to a little bit more complicated questions to the very end. We discussed the properties of, or operations, I would say, operations of Euler form and polar form in complex numbers. So in the next video, what we'll look at is powers of complex numbers. And that is when polar and Euler form are super super efficient, right? That is where you save a lot of time in calculating. And we'll also look at DeMoivre's theorem maybe, or complex roots. So those are, the upcoming concepts in complex numbers. And yeah, so this was all for today's video, and I'll see you in the next one. Bye bye.